math. What are numbers? Does anybody know? I'm sure you know. Wait, don't say it yet. I did tell you last week. What did I say last week? They're concepts, right? Concepts of quantity. That's probably the best definition for a number. But is that a number?
Yeah.
One? Eveline, can you say that number for me in Spanish? Judy, can you say it in Bicol? How about Tagalog? So which one of those is one? Well, but it's not the same word. Why is it consistent? It's a concept. It's a concept, and language is describing that concept. So 1, 2, 5. If we said it in different languages, it's going to sound different. Is this symbol magical? What about these? They can be the same, they're just different representations. The symbol is not the number. If I deleted number 2, 2 does not disappear from the universe. It's just a representation. It's a concept. So when we talk about numbers, you got to recognize it's like these blocks, right? 2 plus 2 is equal to what?
4.
If this was zip, zip, and zip, zip, it would still be the same quantity, no matter what you call it. It's a concept of quantity. Numbers in themselves are actually nothing. And I know most of you think numbers are nothing already, but that's but numbers are just a concept.
Don't talk like that around Dan.
But there's different kinds of numbers, right? You got negative numbers like minus 12. You got big numbers like 12,500. And then you have numbers like 3-eyed. Who knows what the I stands for? It's imaginary numbers. They're not really imaginary, okay? It's a concept. An imaginary number, when you square an imaginary number, it's a negative number. Now, if you know basic algebra, that doesn't seem like it makes sense. Those are real numbers. They just have there's a different concept that it's representing. So imaginary numbers are real. When you square imaginary number, it's a negative number. I know it messes your mind, but it's real concept. Again, it's a concept of quantity that is describing something in the physical world, and this is just a mathematical representation of it. That's all math is. Or numbers is. Numbers are just a concept of quantity that's being used so we can tell the difference between 2 plus 2 is equal to something other than 4. So it brings me to math. What is math? Math is the application of that concept, right? I mean, 2 minus 1 is 1. 2 times 2 is 4. A plus B equals C. They can start getting into algebra. You can get into more complicated things like E equals MC squared. The one at the bottom, that's quantum mechanics. That's a Laplace transform. I can't do that anymore. I used to do it when I was doing that sort of thing. Math can be quite complicated, but again, it is still an application of the concept of quantity to explain the observable world and maybe predict something that would happen in the observable world. Do you understand? You understand how it's a concept of the mind used to explain what we observe or to allow us to communicate about what we observe.
It can be independently discovered in multiple places because nobody develops math. It's just coming to an understanding of how these things work.
It's an excellent thing. I should have said that. Math is discovered. It's not developed. Some people...
Pythagoras' theorem, right? That was independently discovered by the Chinese, by Pythagoras in Greece, and then also by the Egyptians.
Yep.
So there was 3 different theories, but it all explains the exact same thing.
Yeah, and Pythagoras gets the credit, and his was the last one to develop it. You'll figure it. But again, math is just a concept, the application of a concept to explain what we see. So now that's my foundation. Math is less scary than you think it is. It's just a concept of your mind.
What's language?
Exactly. We'll talk about language next week when we talk about what information is. Math is part of that information chain. But I want to just zoom into 2 plus 2 equals 4. Why is 2 plus 2 always equal to 4? Can it ever be 2 plus 2 equal to 5? Are you sure? There are people that will tell you that it can be. And I always want to say, it's like, okay, I'm going to give you $2. My wife's going to give you $2. You give me 5 back. And we can do that all day until you accept the fact that there's a truth in numbers. Okay? I mean, there just is. And that truth has to come from a source. That's the thing that is important in this. There has to be a standard in order for us to have a truth. And the question that we're going to have to ask is, what is that standard? As Christians, we believe it's God. As a naturalist, why is this? And that's a big question for them. So this is kind of where they come to. In the Christian world, we'll talk about the contingent chain that we talked about. We'll talk about how patterns come from a mind. That's the reason there's patterns. We'll talk about the complexity of the universe as evidence for God. And the fact that the physical and the conceptual merge and are consistent is evidence for God. The atheist is going to go down the obvious path. It's going to choose brute facts or necessity and say, it's just the way it is. Because this is the only universe that we got. This is the only one we can observe. It's just the way it is. There's nothing to see here. Then they'll go after our God. And they'll say, well, if you're right, it's almost a conceding that our explanation's better than there. They'll talk about divine hiddenness and the fact that your God doesn't make himself obvious, so why would you think that God is the origin of numbers? And I'm like, I don't think whether the God chooses to make himself known to you is important on whether he's the origin of this information. This is like a bait and switch, a distraction technique. They always go to God of the gaps. They'll say, okay, you say God's the best explanation. Okay, I get it, but someday science will have a better explanation. Today, which one has a better explanation? Because, remember we talked about it on Sunday. God says we need to be focused on him on every day that's called what? Today. 10,000 years from now, they don't know either. They're just imagining it because they don't want the obvious. And then the last resort is always the incoherence. And it's almost a sequence you'll see from the atheist. When they're trapped, they'll just say, well, the way you define God is incoherent with the argument you're giving me right now, so this cannot be the possibility. It's very consistent. So it comes down to this. As a Christian, we say God is the ultimate cause, and we use a cumulative case like we've talked about. We look at the evidence and let the evidence lead us to the truth. An atheist says anything but God. That's their premise at their start. That's their bias. Can you be reasonable if you start with anything but? So the reason's out the window. If they were reasonable, they'd have to leave it in and then prove it's not true. And then they want to use parsimony. We talked about parsimony a few weeks ago. Parsimony just is the simplest answer. That's the best way to say it. I believe parsimony actually proves the Christian worldview, because I think God is a lot simpler answer than thousands of unknown things. That is the atheist worldview. That their simpler solution is the laws of nature, which they don't know yet. That seems more complicated to me. All right, so now you're going to listen to a video. And this is a guy from Answers to Genesis. It's about 15 minutes talking about the Mandelbrot set. Some of you know this video. You're going to enjoy this.
I dare say there is no secular or atheistic explanation for what I'm going to share with you. This secret code only makes sense in the Christian worldview. What if there were a code embedded in numbers like 1, 2, 3, 4? What if there was a secret code embedded in them that we finally got around to discovering? What would that imply? What if there was a message inside numbers? What would that imply? It would tell us something about the intelligence of the person who made numbers. Now, we don't often think about God creating numbers because they're abstract. We think about God creating animals and stars and planets and so on. But numbers, God is responsible for them as well. Even though they're abstract and conceptual, God's sovereign over the abstract just as much as he is the physical universe. And as a matter of fact, there is a secret code built into numbers, and it is mind-blowing. And this is something that I read about when I was pretty young, really, and it was mind-blowing to me. And I want to share this with, it's called the Mandelbrot set. This was discovered in the late 1970s, early 1980s, named after the person who really discovered this, Benoit Mandelbrot. He was a math guy and a computer guy. He worked at IBM. This set is defined according to this little formula that you see right here, where it's the set of all numbers, C. C is a number that is potentially part of the Mandelbrot set. We're testing it, for which this other number, Z, remains small according to this little formula. And it looks very complicated, but it's really not. I'll take you through it. What we can do then is we can make a map, because I'm trying to figure out if there's a pattern to the numbers that belong to the Mandelbrot set. And it turns out there is. But it's not obvious, right? Because you can't tell just by looking at a number whether it's going to belong or not. You have to run it through that formula, and that's kind of tedious. But in the 1980s, computers were starting to get fast enough where they could iterate that formula a number of times, and they could analyze to see whether Z is getting big or staying small. And so what we can do is we can have the computer check all these different points, and we'll see if there's a pattern to the Mandelbrot set. And so we'll take the points that belong to the Mandelbrot set, and we'll color those black. That's arbitrary. That's the way Benoit Mandelbrot did it, and we follow his example. So, and you have the computer check more points, and you find that all those points right there belong to the Mandelbrot set. When you run it through that formula, Z stays small. And then the points that do not belong, we'll color those red, or some other color. It doesn't really matter. And so we already checked the point 1. We found that the number 1 does not belong to the Mandelbrot set, so it gets colored red. And had we checked these other points, we would find that they do not belong. And so you see, as you plot more and more of these points, a pattern starts to emerge. What's it going to look like? Well, you have the computer run through thousands and thousands of points. You have the computer check each one of those numbers, and a pattern emerges, and the pattern looks like this. It's really interesting and unexpected. Nobody was expecting that when you made a map of the Mandelbrot set, it would look like that. Remarkable. I'm going to remove the axes now, because it turns out this shape is remarkably interesting and unexpected, and it'll turn out to have a lot of beauty in it as well. The shape itself is, I mean, this is a mathematical plot. I guess we'd expect it would have some mathematical properties to it, but everyone was surprised by the properties it has. The main shape that looks kind of like a heart, that's called a cardioid. And a cardioid is what happens when you take a circle and you take your pencil on it and roll it around another circle of equal size. The shape you'll get is a cardioid. And you can see that, sure enough, the main part of the Mandelbrot set is a perfect cardioid. All the other shapes that are growing off of it are circles. All these perfect circles attached to the perimeter of the Mandelbrot set. And then you see some other features, like these little tendrils that grow off of it, and a spike over on the left, kind of that juts out. That's kind of interesting. You notice that that top circle there, it's got a circle on top of it, another one on top of it, on smaller and smaller scales, and it goes out and forms this little tree, and it's got 3 stems to it, including the trunk. So it's got a trunk and 2 stems for a total of 3 branches. You see that there? Now the next one to the left branches into 5. Can you see that? I mean, it's kind of small, but you can see the 5 branches there. The next one is 7, 9, 11, 13, 15. It's all the odd numbers. And by the way, they don't stop. They go to infinity. There's an infinite number of them. They get smaller and smaller, though, and so you have to zoom in more. So somehow the Mandelbrot set knows how to count. It's kind of remarkable. And then on the other side, you have the odds and the evens. You have all the numbers there in terms of the number of branches. Now, it's remarkable enough that they have branches at all, because who would have thought that when you run numbers through that little formula, you get that shape? It's remarkable. Nobody was expecting that. And it's even more remarkable that it has the ability, apparently, to count in terms of the number of tendrils that grow off of each bud there. And, of course, you can take 2 of those numbers, like 5 and 3. Now, 5 plus 3 is 8, okay? And it turns out that the bud in between those 2 has 8 tendrils. Interesting. And that's true of all of them, both on the left side and the right. The bud in between the two adds the number of tendrils on each one. So not only does the Mandelbrot set know how to count, it knows how to add. And then on the left side over there, you got this kind of spike that goes out. And you see there's this little bump on the end of the spike. So let's take a look and see what that looks like. So we'll zoom in on it. And that little bump, turns out, it looks like the entire Mandelbrot set. It's a mini Mandelbrot set. And it's almost identical to the parent, except it's got extra spikes growing off of it. But the basic shape's the same. It's got the cardioid and the circles. And, oh, it has a little spike growing off of it, too, with a little bump. What could that be? Well, let's zoom in on that. And, oh, interesting. Absolutely fat, and it's got extra spikes growing off of it. And that's got a little bud. How about that? Now, of course, you could do that literally forever. And there's an infinite number of baby versions built into the Mandelbrot set on smaller and smaller scales. And take a look at how small this is compared to the original when we zoom back out here. Look at how tiny it is. Isn't that remarkable? And the fact that it repeats infinitely, and it doesn't lose complexity, it actually gains it each time you get more extra spikes growing off of it. Very remarkable. Well, to anticipate my conclusion in this, I'm going to suggest to you that this shape tells us something about the way God thinks. God's understanding is infinite. Numbers are an aspect of God's mind. God is responsible for numbers. And so it makes sense in the Christian worldview that when we explore and study numbers, we find intelligence in them. We find evidence of patterns. And not only intelligence, but infinite intelligence, because this thing repeats infinitely. A structure that repeats itself on smaller and smaller scales is called a fractal. So the Mandelbrot set is one example of a fractal. There are other types of fractals. There are other sections of the Mandelbrot set that are fractal. We could zoom in, for example, on one of these little tendril features here and zoom in on that. And you'd say, well, that's interesting. You think what's going to stop at some point, right? Eventually it'll even out and but it just keeps going. It's infinitely wiggly, you see. It's wiggling around like that, and you zoom in on it, and it keeps going and keeps